Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are strapping ourselves into one of the densest and most critical fields in engineering, the world of mechanical shock and vibration.
This really is the domain that separates theory from reality. We're taking a deep dive into some extensive excerpts from engineering handbooks, the kind you usually need a decade of experience just to navigate, to give you a shortcut.
So our mission today is to get you informed and quickly on everything that shakes, rattles, or rolls. We're going to move from the foundational theoretical analysis through all the cutting-edge measurement tech and finally into the practical control of these problems.
The scope is pretty intentional. We start with the analysis fundamentals, covering the contrast between simplified rigid bodies and these complex continuous structures. Then we'll shift gears entirely into instrumentation, the transducers, the signal processing, all the data cleanup techniques that let us actually see the problem.
And then we'll wrap up with the applications.
Right? Critical applications, things like machine monitoring, specialized testing, like the shock response spectrum, and even how we model the human body under impact.
That model treating the human spine like a spring, that's where it gets really interesting later. But okay, let's start at the beginning. Analysis. When engineers look at a vibrating system, they immediately categorize it, right?
Exactly. You've got two massive categories. First, systems defined by what we call lumped parameters. Think of a heavy machine sitting on big rubber isolation pads. You can simplify that, treat the machine as one rigid mass and the pads as separate springs and dampers.
So all the important properties are in discrete or lumped places?
Precisely. And even if you have several modes of vibration coupled together, the math is still manageable because the parameters, mass, stiffness, damping, are all just discrete values.
But then you have the other kind of structure, where the mass and elasticity aren't so conveniently located.
And that brings us to distributed parameters. This is where the mass and the stiffness are spread throughout the entire volume of the material. Think beams, plates, shells.
Okay, so you can't just use a single equation of motion anymore.
Not at all. You have to start solving partial differential equations. The whole analysis fundamentally changes. You move from algebra to continuous calculus to describe the motion.
And as soon as you start modeling these complex systems, especially under forcing, you run out of that comfort zone of linearity pretty fast.
Oh, nonlinearity is the standard in the real world. I mean, a key distinguishing feature of nonlinear free vibration, and it's a huge red flag, is that the period of the motion actually depends on the amplitude.
So if I have a simple linear pendulum, it doesn't matter if I swing it a little or a lot. The time it takes for one full swing stays the same. But for a nonlinear system,
Push it harder, and the duration of the swing changes. It's that relationship between amplitude and frequency that's so key, and that spills right into forced vibration. If you plot the response curve for a system with nonlinear restoring forces, maybe a structure that stiffens or hardens, the resonance peak doesn't just shoot straight up.
it bends.
It bends or gets swept over. In a hardening system, the peak leans to the right, toward higher frequencies. In a softening system, it leans left. And damping still does its job. It limits the amplitude at resonance, but the geometry of these curves is what makes them so unique.
And as long as we're talking about these continuous systems, we have to look at rotation. Torsional vibration, that twisting motion, is just fundamental to things like engine crankshafts.
Torsional issues are their own specialty, but they're built on the same foundations. When you model a rotating system, you have to account for how the mass is distributed. And that means calculating the polar moment of inertia, J.
Which is J, calculated as the integral of r squared dm. It's a measure of how far the mass is from the axis of rotation, right?
Exactly. And if you get that wrong in a reciprocating engine, you're looking at catastrophic shaft failure. And very quickly, it connects the math directly to durability.
So we've laid out the theory. Now, how do we actually measure these complex motions? Let's move to the art of measurement. The primary tool here is the accelerometer, isn't it?
Absolutely. For acceleration, the accelerometer is king. But, there are major trade-offs in how they're built, depending on what you need. We mostly use two types, piezoelectric and piezoresistive.
Okay, tell us about piezoelectric first. Those are the self-generating ones.
Right. They rely on the direct piezoelectric effect. You stress a material, it generates a charge. They're real workhorses, especially in extreme environments. Using materials like tourmaline and lithium niobate, we've developed sensors with incredible thermal stability. We're talking reliable measurements from minus 425 degrees Fahrenheit up to plus 1400.
That is an insane range. Why is that so important?
Because even a tiny change in the material properties can throw off the sensitivity. But beyond temperature, there's a huge practical advantage in the signal conditioning. We prefer charge sensing because the sensor sensitivity becomes independent of your cable capacitance. Well, up to a limit anyway.
That's the real-world insight. If you're running a long cable through a factory, you don't want the cable itself screwing up your signal.
Exactly. It makes deployment so much more robust. Now, you contrast that with piezoresistive accelerometers. They are not self-generating.
How do they work then?
They use semiconductor materials, usually silicon, where the electrical resistivity changes dramatically with strain. They need external power, but they offer fantastic sensitivity, even down to DC. The trick is in the circuitry.
The Wheatstone bridge.
Precisely. You arrange the sensing elements in a Wheatstone bridge, often with 4 active elements. This does 2 brilliant things. 1, it dramatically increases the sensitivity, and 2, it cancels out errors caused by temperature changes.
That cancellation is such an elegant piece of engineering. Now, every sensor has its limits based on that ratio of the vibration frequency to its own natural frequency, omega over omega n. I was surprised just how restrictive an undamped accelerometer is.
It's severely limited. An accelerometer with 0 damping is only accurate up to about 20% of its own natural frequency. Any higher, and the errors just explode.
So you're forced to pick a sensor with a ridiculously high natural frequency just to measure something in the mid-range. How do you extend that usable range?
With damping. But not just any amount. If you increase the fraction of critical damping to about 0.65, you get this mathematically optimized flat response. That one change extends the measurable range all the way up to about 60% of the natural frequency. It's a huge improvement.
Okay, so we've measured the motion, we have a signal, but we live in a digital world, so that signal needs to be sampled. And this brings us to that first major data problem, aliasing.
Aliasing is data corruption. I mean, pure and simple. When you digitally sample a signal, if you sample too slowly, slower than twice the highest frequency in your signal, the spectrum overlaps on itself.
And the high frequencies get falsely mapped onto the low frequencies. It just looks like noise, but it's actually corrupted data.
Exactly. And you can't undo it. That's why the anti-aliasing filter is so essential. Its only job is to make sure before the signal gets digitized that no frequency components exist above half the sampling frequency. These filters need to be incredibly steep. We're talking 120 decibels per octave to cut things off cleanly.
It's the digital gatekeeper. So let's say we're monitoring a machine, maybe a gearbox, and we have a good signal, but it's buried in all this factory noise. We can use a technique called synchronous averaging.
A very powerful technique. The key is synchronization. We use a repetitive pulse, maybe from a sensor that triggers once per revolution of a shaft, to start recording our data.
So the specific vibration signature you're looking for is always recorded starting at the exact same point in time.
Precisely. And when you average all those recordings, the real repetitive signal from that gear fall, say, adds up directly, proportional to n, the number of averages. But all the random background noise, all the non-synchronous stuff, it only adds up like random noise, proportional to the square root of n.
So you're improving the signal relative to the noise.
Yes. The overall improvement in the signal-to-noise ratio is proportional to the square root of n. So you average 100 times, you get a 10-fold improvement in clarity. It's invaluable for pulling a tiny signal out of a mountain of noise.
Okay, that gives us a clean signal. Let's move to testing and control, starting with shock. When we test something against an impact, say dropping a phone, we use the shock response spectrum, or SRS.
The SRS is, well, it's the fundamental way to characterize a shock in terms of its destructive potential. It's a plot that shows the maximum response, acceleration, velocity, whatever, that a simple single-degree of freedom system would experience as a function of its own natural frequency.
So if I have a component that naturally vibrates at 100 hertz, the SRS tells me exactly how hard that 100 hertz component was hit by the shock.
That's it. Exactly. And while you can plot it different ways, velocity is often the preferred parameter when you're thinking about damage potential.
Why velocity?
Because the maximum stress inside a structure is directly proportional to the modal, or the relative response velocity. So if you're designing for material strength, the velocity SRS gives you the most direct prediction of failure.
That's fascinating. Let's swing back to condition monitoring for machinery. If a local fault, like a tiny crack on a gear tooth, starts to develop, how does that show up in the data we just cleaned up?
It shows up in a very reliable pattern. You'll see the main vibration peak of the gear, but it'll be surrounded by a family of smaller peaks called sidebands. And the spacing between those sidebands is the key. It's exactly equal to the rotation speed of the faulty gear.
Because that cracked tooth hits the mesh once per revolution.
Precisely. And we use specialized techniques like cepstrum analysis and envelope detection to reliably diagnose and track these defects before they cause a catastrophic failure.
Now, for active control. If we have a machine that vibrates at one specific frequency, the classic countermeasure is the auxiliary mass system, the tuned damper.
The tuned damper is a mechanical masterstroke. It's just a small secondary system, a spring and an auxiliary mass, that you tune so its own natural frequency is the same as the disturbing frequency of the main structure. When the machine starts to vibrate, the damper starts vibrating 180 degrees out of phase, and it applies an equal and opposite force.
Effectively neutralizing the vibration.
Right, at that one specific frequency. We've seen them used successfully on machine tools, for example, where a plastic ring element can combine both the elasticity and the damping into one single unit.
Which is different from a system where the mass is coupled only by damping, like with viscous fluid.
Yes, a purely damped system is focused on absorbing and dissipating energy across a wider band, not neutralizing a single frequency peak like a tuned damper does.
Let's shift our focus to extreme environments. Structures don't just respond to their own forces, they respond to the whirlwind, fluid flow, high-intensity sound.
High-intensity acoustic fields are a huge deal in aerospace. The sound pressure from a rocket engine alone can cause fatigue failure. But maybe the most dramatic fluid interaction is vortex-induced oscillation.
The classic example being a cylinder in a crossflow, like a bridge piling.
Right. As fluid flows past, it creates these alternating, swirling vortices, the von Karman vortex street. The frequency of that shedding F sub s is proportional to the flow speed.
And the trouble starts when F sub s approaches the structure's natural frequency, F sub n.
That's the critical point. As the flow increases and F sub s gets close to F sub n, you get this phenomena called lock-in. The shedding frequency stops increasing and instead locks onto the structure's natural frequency. This causes huge vibrations, and the maximum amplitude typically happens around a flow velocity ratio U divided by FD of about 5.5.
And finally, let's consider the most complex system we analyze under shock, the human body.
For scenarios like a car crash or an aircraft ejection, we use something called the Dynamic Response Index, or DRI. It's a tool for estimating the potential for spinal injury.
It seems almost reductive to model the spine that way, but you have to start somewhere.
You do. The DRI is based on a highly simplified single degree of freedom model of the spine. The index itself is defined as omega n squared times delta max, all divided by g.
And are there specific parameters for this analytical spine?
Yes. Based on tons of experimental data, the model uses a natural frequency, omega sub n, of 52.9 radians per second and a damping ratio, zeta, of 0.224. Those specific numbers define the model used for safety standards globally.
And those numbers lead directly to safety criteria.
They do. For instance, a DRI value of 18 suggests about a 5% probability of spinal injury based on historical data. It's an incredibly practical metric, even though the model itself is a massive simplification.
It's really remarkable. We've gone from the abstract math of distributed systems through the physics of piezoelectric materials, all the way to a specific number, like 52.9 radians per second, used to predict human safety. We've covered the entire mechanical landscape.
Well, what's fascinating is the tension between these practical linear models we use and the underlying reality of the systems. For the DRI, we treat the body as a linear passive system, which is okay for small amplitudes. But soft tissues like muscle and tendon, they aren't simple springs. They're more like viscoelastic elastomers, and they show considerable nonlinearity, even well below the point of injury.
That nonlinearity seems to be the ultimate challenge. We use linear analysis to get our heads around the basics, but whether it's a hardening spring, turbulent flow, or the tissues in your own body, the world around us is defined by that elusive, difficult to model, nonlinear behavior. Thank you for guiding us through this.
Always a pleasure.